Survey of Calculus, Chapter 2, Section 1. Using first derivatives to find maximum and minimum values, and sketch graphs. Okay, we're going to start with a definition. That definition says that if you have a function, it is increasing over I, a given interval, if for every a and b in that interval, when a is less than b, then the function value at a is less than the function value at b. Or in other words, when your one x value is less than another, then the y value for that smaller x is smaller than the y value for the larger x. Here's an example. You can see where a is, f of a, b and f of b. And you see that a is a lower value than b, and f of a is a lower value than f of b. And when that happens, then your function is going to be increasing or going up as we look at it from left to right. Here's another way of putting it. If the input A is less than the input B, then the output for A has to be less than the output for B. Now here's a second definition. We have a function f that is decreasing over an interval I if for every a and b, those are x values, in that interval, if a is less than b, then f of a is greater than f of b. Visually, here's what it looks like. And notice we're using G here instead of F. That's okay, same thing. Here our A, our X value that is A, is smaller than our X value that is B. However, when we put A into the function, we get a bigger value for Y than we do when we put B into the function. And what that results in is the function will decrease or go down as we look at it from left to right. Remember that the derivative of a function is very simply the slope of the tangent line for that function at any given point. When a graph increases, its slope will be positive, and when it decreases, the slope will be negative. This allows us to make conclusions about where the function is increasing or decreasing based on the derivative of that function. So Theorem 1 tells us if f is differentiable, in other words, you can take a derivative at any point over an open interval I, if the first derivative of that function is positive, then the function is increasing over that interval. If, however, the first derivative for that function for all x values in the interval is negative, then it is decreasing over that interval. So let's look at the graph here. Notice that the derivative is 0 at these points, at C1, C2, C4, C7, and C8. Also note that the derivative doesn't exist at the points I didn't mention, at C3 because it's a vertical tangent. At C5, you've actually kind of got, it's coming off of a vertical tangent, but then it's a corner. And at C6, again, you've got a corner. Those points are called critical values. And the reason for that is you will notice at those points, things are happening with the graph. Things are changing with the graph. At most of those points, the graph is changing direction. It's going from increasing to decreasing or decreasing to increasing. So here's our next definition. A critical value of a function f is any number c in the domain for f for which the tangent line is horizontal or for which it does not exist. In other words, our critical values occur at x values where the first derivative is either 0 or does not exist. Because if a function is going to change from increasing to decreasing or vice versa, it's only going to change at a critical value. It's either going to change when the derivative is 0 or does not exist. So we're going to check those points. We're going to find where it's 0 and where it doesn't exist because most of the time something interesting is happening around that point and we want to find out what's going on. Now, that doesn't mean it has to change at the critical value. It's just that if it's going to change, it will change at a critical value. C1 and C3, we've got a couple of critical values here, and they are examples of relative minimum. In other words, they are both the lowest points in the vicinity for that little interval, for those intervals on that graph. And C2, f of C2, is a relative maximum because it is the highest in the vicinity on that graph. And collectively, these relative minima and maxima are known as extrema. The singular for that is extremum. All right, and some more definitions now. F of C is a relative minimum if there exists within I an open interval, I1 containing C such that f of C is less than or equal to f of x for all x in I1. In other words, f of C is a relative minimum if it's the lowest point anywhere near that point in that interval. So it may not be the lowest of the lows, it may not be the lowest point in the entire graph, but for the surrounding area, it's the lowest point. And then a relative maximum has a similar definition. It's just going to be the highest point in that surrounding area. Again, a relative meaning it's not necessarily the highest or the lowest for the entire graph. However, for the surrounding area, it is the high point or it is a low point. Okay, note that the x values where the extrema are located are those values for which the derivative is either 0 or does not exist. I'm repeating this. Whenever something's repeated like this, it's very important. The places where the derivative is 0 or does not exist are very important points. So you need to keep in mind, it's really important to figure out where the first derivative is 0. So if a function has relative extreme values over an open interval, then it's going to be at a critical value, which means the first derivative at that point will equal 0 or will not exist. If we want to find minima or maxima, we need to check the derivative and determine whether it either doesn't exist or where it doesn't exist or where it equals 0, which are called the critical values. But again, not every critical value is necessarily a maximum or minimum. So let's say we go and we take the derivative and we figure out where the first derivative equals 0 or doesn't exist, okay? That tells us those are potentially extreme points, but how do we know for sure? Well, I'm glad you asked. To determine this, we need to understand how the graph and the slope act on either side of an extreme value. Are kind of helping us get an idea of what happens. You'll notice here in the first row, we've got C. C is a relative minimum, and notice what's happening with the tangent line on either side with the slope. On the left side, the slope is negative, and on the right, it's positive. So what that kind of leads me to believe is that if I can find where the derivative is 0 or doesn't exist, and then I look on either side of it, on the left side, a point, a number put into the derivative should give me a negative. On the right, it should give me a positive if that's a minimum. Now look at the maximum. On the left side of the maximum, the slopes are positive. On the right, they're negative. Now let's look at the third row here. Okay, here the derivative would indeed equal 0 because it flattens out. However, notice that on both sides of it, the slopes are negative. What that tells me is that that's not a minimum or a maximum at all. It's just kind of a flattening out point, and the graph keeps going down in the same direction it was before it hit that point. And then we see the same thing on the last row there, except with an increasing function. There is no change in sign on the derivative on either side of C. So that gives us Theorem 3. Theorem 3 says that if you have a continuous function that has exactly one critical value in an interval, not over the whole function, but in an interval. It says that, first of all, the function has a relative minimum if the derivative is negative on AC and it is positive on CB. In other words, if it is negative on the left side, but then positive on the right, it's decreasing to the left, increasing on the right. The second part says we have a relative maximum if the derivative is positive on AC and negative on CB. In other words, if it is positive on the left and negative on the right, or it's increasing on the left and decreasing on the right. And then part 3 just tells us that if there's no sign change on the derivative on either side, then you don't have a relative maximum or minimum. In other words, it summarizes what we just talked about on that chart in the previous slide. What we're going to do is we're going to graph the function and find the relative extrema. Pause the recording and use what we just talked about, give it a try, and then resume to check your answer. Okay, so suppose we're trying to graph this function, but we don't know any calculus. Well, what will we do? Well, we plot a few points and determine which direction the graph seems to be turning. So the first thing they're going to do is kind of do this. And so they plotted a bunch of points, and there we go. Okay, so that's kind of what the graph looks like. We could see some of the features of the graphs from the sketch, but you know, if you're trying to do it that way, unless you just kind of get lucky, you may not hit the actual turning points. So we're going to do it using calculus now. We're going to find a general expression for the first derivative, which is 6x squared minus 6x minus 12, and we're going to figure out where this equals 0, or where it doesn't exist. Now this is a polynomial, so it's continuous, it's going to exist. So the does not exist part is not really an issue here. So we set it equal to 0, and the first thing we did is divide everything by 6, and then factor, and we get 2, and we get negative 1. And then what I like to do is I'll create a little number line and put 2 and negative 1 on there, and it divides it up into 3 regions. Okay, and so A is from negative infinity to negative 1, B is negative 1 to 2, and C is 2 to infinity. So what we're going to do is we're going to test a point on each side of the negative 1 and the 2, and in between them, and see where the derivative is positive and where it's negative. And so that's what we're doing here. So we're going to test negative 2, and when we put that into our derivative, it's positive. When we test 0, which is between negative 1 and 2, we get a negative. And then when we test 4, which is outside of 2, we get positive. And what that tells me is that negative 1, the left is positive, so it's going up. To the right, it's negative, which means negative 1 is going to be a relative maximum. And then for 2, it's negative on the left and positive on the right, so it's going to be a relative. What I actually like to do is I'll actually even kind of sketch that. I'll show you how to do that in class, but I like to make a little sketch of it and actually be able to visualize what's going on there. So we have that there is a relative maximum at negative 1, and to find the y value, we put negative 1 into the original equation. And we have a relative minimum at 2, and again, to find the y value, we put it into the original equation. All right, let's try another one. Same idea. Pause the recording, give this a try, resume to check your answer. So you can see there's the graph of the function, and you should have gotten a relative maximum at negative 348 and a relative minimum at positive 360. All right, now try to find the relative extremes for this function. Pause the recording, give it a try, and resume to check your answer. And then sketch the graph. Okay, so the first thing we're going to do is the first derivative. And again, you don't need to simplify this. Here they, kind of took care of the negative power and all that. You can leave it in the first form. Okay, Okay, so we're going to figure out where the first derivative doesn't exist or equals 0, and that is going to be at x equals 2. That's where the denominator would equal 0, which is where it would not exist. And there's really, it says f of x equals 0, or the derivative equals 0 where the numerator equals 0. Since 2 is not 0, then the numerator will never equal 0. So we have one place to check, and that's when x equals 2. And again, you see our little number line, and so we went through and checked. We tried 0 into the first derivative and got a negative, and then we tried 3 and got a positive, which means that 2 is going to be a relative minimum. And then we put 2 into the original problem and we get 1. So the 0.21 is a relative minimum. And here's what the graph looks like. You can see why the derivative doesn't exist even though the function does. We've got a sharp corner there. All right, let's try another one. Pause the recording, give it a try, and resume to check your answer. Okay, so find the first derivative and figure out where it equals 0. We have 2 points to check. We have x equals 0. Again, draw your number line and partition it off and try points on either side of 0 and 2. And what we find is that when we tried -2, it was decreasing. When we did 1, which is in between 0 and 2, it was still decreasing. So that tells me 0 is not actually a minimum or maximum. It just kind of flattens out for a little bit. And then we tried 3 and it was increasing. So it's decreasing until it reaches 2, and then it's increasing, which tells me that 2 is a minimum. And then putting 2 back into the original equation, you get -16/3 for the y value. See at 0 how it does flatten out, which is why you get the 0 derivative, but it doesn't actually change direction there, so you don't have a minimum or maximum. All right, one more. Give it a try. Pause the recording. Check your answer when you're done. So the first derivative, we have -1/3 x to the -2/3. And then the reason there, you don't have to simplify it, but putting it under like this reminds us that we do have a denominator here. And so we need to check to see where it doesn't exist, which would be when x is 0. And that's the only place where we have 0 or does not exist for a first derivative. So we're going to try on either side, and we see that there is no sign change. Because there's no sign change, it's decreasing over the entire range. There is no maximum minimum. When you look at the graph, you see why the derivative doesn't exist there. It's because we have a vertical tangent. And here's our section summary. You might want to pause and look over this and resume when you're ready to move on. Okay, the rest of this is additional practice. So if you'll try these problems, pause the recording while you're doing them, and resume to check your answer, and do that for the remainder of the recording.